So for those of you who do not know me, my name is Amber, and I am one of Dr. Lambert's PhD students, so I'm going to be substituting in his class for the rest of this linear algebra portion of this course. So I'm not sure, it's going to be about a month and a half or so. So I'll be with you in the classroom and also in the labs. Of course, Dr. Lambert is here, so he's available for any questions that you have about homework or whatever you want to talk to him about. We're still going to record the lectures just as you always do. So today we're starting the linear algebra portion of this numerical analysis class. Now, when we talk about linear algebra, the first thing that we discuss is solving linear systems, right? And so when you took a class like linear algebra, here it's MAT 326, you learned about solving systems of linear equations. So how did you go about doing that in that class, or in a linear algebra class? What do you do to solve a linear system of equations? Yeah, Gaussian elimination to get it in what kind of form? You don't have to use the correct terms. But what do you? Well, yeah, you can use an augmented matrix, but what do we want it? What do we want it to look like?
Row echelon.
Right, row echelon, reduced row echelon. So row echelon form is a diagonal or a triangular matrix, and then reduced row echelon form, you essentially reduce it to the identity matrix, and then you can just set your unknowns equal to the right-hand side. So the first thing that we're going to look at is in section 4.1 of the notes, and if it's not up right now, it will be up soon. So section 4.1 of the notes is on triangular systems of equations. So the basic idea behind solving a system of linear equations is to reduce your linear equations to linear equations involving a single unknown instead of having a bunch of unknowns in one equation. So when you have one unknown, then you can solve for that one unknown. Because these equations are trivial to solve, these types of equations make up what we call triangular systems, and there's three types of triangular systems. The first type is the most important. It's what we're going to focus on today at the beginning of class. Is upper triangular systems. So if we have an upper triangular system of equations, this corresponds to 1, then it looks like this, where everything below the diagonal is 0. So what's one way that we could represent the elements aij? Which ones are 0, according to the indices I and j? Okay, so if we have I equals 1, j equals 1, that element is not 0, but here, let me write this, 1 and 1. Here j is 2, and here
So
I is
1.
2. So 2, 1 is 0, so if I is what?
Greater than.
Right. So for all aij is equal to 0 for I greater than j. Okay. So the second type, now we'll talk about a little bit today, is diagonal system. So a diagonal system is just a diagonal. So everything else that's not on the diagonal is 0. So how would we describe the elements aij, the ones that are equal to 0 in this case? Right. aij equals 0 for I not equal to j. And then lastly, is lower triangular systems. So we have the diagonal, and everything below the diagonal is non-zero. and everything above the diagonal is 0. So how would we express the elements that are 0 in this circumstance? We have aij equal to 0 for what?
I less than j, right?
Right, I less than j. So those are the 3 types of triangular systems, and those are essentially what we want to reduce our problem to, because these are the systems that are trivial to solve. So since they're trivial to solve, we're going to talk about how do we solve them first. It's going to take me a while to get used to this. Alright. So upper triangular systems are the ones that we're most interested in, because when we have a matrix and we do Gaussian elimination, then we're trying to reduce it to an upper triangular system. So we've already seen what the structure of a upper triangular system looks like. So we're just going to illustrate the process with a general system. So we have an example, a11x1 plus a12x2 plus a13x3 equals b1. Now, since this is a triangular system, this element's going to be 0. So the next one that we have is this. And then here we only have one element, a33x3 is equal to b3. So this is this type of system that we're interested in looking at. How do we solve this? And then we're going to come up with an algorithm for this, for solving these types of systems. So if I'm trying to solve this system of linear equations, not thinking about Gaussian elimination and all that, because we already have it in the form that we want, what would you do? Which one would you start with? Right, we'd start with the last one. Oops. And what do?
Express x3 in terms of
Right, so what?
constant.
Then we just divide. Because x3, the x's are unknown, so that's what we're trying to solve for. So we solve this equation for x3. So then we have x3 equals b3 over a33. So that's one of our unknowns. So now that we have found this one, we can use it and substitute into the equation above it. And then in this equation, we only have one unknown, which would be x2. So let's go ahead and do that. And so we're assuming now that we already know x3. So I'm just going to still use x3 instead of complicating the expression by saying b3 over a33, because b3 over a33 is just a number called x3. So now we've got a22 x2 and then we want to solve this one for x2, so we subtract, and then we would divide. So we've got x2 is equal to b2 divided by a22. So that's going to give us our expression for x2. So here's x3, x2. And then the last one that we'll need to solve for is x1. So now we know x3, we know x2. We can plug them in and solve for x1. So a11 x1. Okay. go ahead, I'm not going to rewrite all of that, but, and divide by A11. So our expression for x1, we have our right-hand side, we subtract the 2 from the left side that did not depend on the unknown, and then divide by the constant of the unknown. So now we have an expression for all 3 of our unknowns. So we've solved the system. So now we have a solution. So we just described a process that we use after Gaussian elimination to find the solution to a system of equations. Does anybody know what this process is called? It's called back substitution. Let's see, can we see over here? So the process that we just described is called back substitution, and it's used on an upper triangular system of equations. So now that we've seen how it works, we can come up with an algorithm.
So this could be used to other systems as well, right?
What do you mean by other systems?
Like diagonal or lower triangle.
Well, this is specific for upper triangular. So diagonal is actually a little bit simpler, and in upper triangular systems, lower triangular systems, we use something called forward substitution. But it's the process that it follows is essentially exactly the same thing. So alright, so we'll start trying to outline this algorithm. So we've got a loop. It's going to start with 4. Now, looking at our example, where did we start? Did we start in rows or columns? And if we did, which one, which row, which column did we start with? So we started in
The last row.
right, the last row and the last column. So we're going to loop over the rows first. So I'm going to say 4i equals n, and then it's going to go n minus 1, all the way up to 1. Now, after we loop over the rows, we also have to loop over the columns, right? But before we get to that, what's something in common that all of these have in common that we do? Well, we don't always subtract with them, right? And the division we need to do after we subtract, because we've got division and subtraction. But we don't subtract in this one, so we need to do the division after the subtraction. But the first thing that we want to do is we've just got this side equal to this side, so we're going to set both sides equal to each other first. And in this algorithm, y is going to be represented by the updated right-hand side. Yeah. Y is the vector containing the right-hand side of the equation. X is our unknown. A is, of course, our matrix elements. And I'm going to use U2, and U is going to describe anything that's in the upper triangular part of the matrix, okay? Alright, so the first thing that we want to do is we want to set our left-hand side equal to our right-hand side. So I've got xi equal to yi. Now, after this, we want to loop over the columns. So I'm going to have another loop. for j equal, and I'll end this one right here. Okay, so with my columns, how do I get my column indices? If I'm in the nth row, which column do I want to be working on? So if I'm in the nth row, then the column, so for the first one, so, okay, let me see. So inside this loop, I'm going to be doing my subtraction, right? Like I'm going to subtract off whatever's left over here, whatever doesn't involve the unknown. So this one, we start in the we start in the nth column here, but let's take a look at this one right here. With the step that I do inside this loop, right, we're going to be...
That's not in the nth column, if we're working in the nth column.
Right, so if n is 1, so I'm sorry, if n is the last, so let's say we're right here. So this is the n minus 1th row. So the column that we're going to be subtracting everything off of is the what? Right, so it'll be the nth. So if this is n minus 1, we're subtracting off the nth. So in terms of I, because we don't want to use n in our loop, then it's going to be I plus 1, right? Because I is equal to n, so then we add 1 to that to get to the next column. So j is equal to I plus 1, I plus 2, and then we're going to go all the way up until n. So in this circumstance, in this one, we only have one iteration to go through here. So we only have, because this is n minus 1, so then we would subtract off just 1 to get to that next, to get to n. So does that make sense to everybody? How we loop over those?
Okay, so if I is n, we're in the nth column.
Right.
So when you have j is I plus 1, that's going to be n plus 1?
Right, so it's going to skip over this part for that row.
Okay.
So then when you get to like n minus 1, then that's where it goes through this loop. But it's only going to go through one iteration because it'll reach n at that point. Okay? And that's what we want it to do too, because what we're going to do in this loop is not going to happen to that last row right there. So what are we actually doing in this loop now? So we've got, let me say xi is equal to xi minus, and what are we subtracting off? So this is just to set up, we have our original and then we're subtracting something off of it. So what do we subtract off here?
H2, x2.
Right, so we're solving for x2 right here. So here I have the right hand side minus aij x, and then what's our x?
xj.
Right, so it'd be aij xj. So now we're almost done with this, but after I've subtracted everything off, what do you have to do to solve for your unknown? Right, so this keeps xi updated, so now xi is updated to be all of these subtracted off. Let's do this here. So xi is going to be xi, and then we're dividing by which elements of the upper part of the triangular system? We've got A33, A22, and A11. Right, so we can call it AII or UII. So we're always dividing by that diagonal element. Alright, so now this is back substitution.
So as you have to put the end before that final.
Because this right here, we don't necessarily subtract something off of every single row, particularly that last row. So we want to do our division as the very last step after we do all of our subtraction. And so just to make sure that it hits that last row, we have to do it outside of that loop. So this is back substitution. And this is the algorithm that we'll use after we get our matrix into diagonal form. So when we get our matrix into diagonal form, we'll use Gaussian elimination to do that. All right, so are there any questions about that so far, about back substitution?
Matrix in diagonal form or upper triangular?
Upper triangular form, sorry. Or we could get into diagonal form, but that's not really something that we do in numerical methods just because it costs so much to get our matrix into that type of form. It's easier to get it into upper triangular form, like you corrected me for. So then we can use this back substitution. So let's talk about the number of floating point operations that this would cost for a minute. I don't know if y'all have seen how to figure out how many floating point operations an algorithm will cost you, but if you just look at the number of nested loops, that's going to be your exponent. So here, the number of floating point operations would be n squared. And when we take a look at Gaussian elimination, we'll see why we don't want to keep eliminating further to diagonal form, because it's much more expensive to do that than it is to just use back substitution once we get in an upper triangular form. So like I said, since we have two nested loops, then that gives me n squared floating point operations. All right. We can take a look at diagonal systems for just a quick minute, and then we're going to move on to Gaussian elimination. So diagonal systems, I've got anything, so if I had A11, A22, A33, and an augmented matrix B1, B2, and B3. Well, it's really trivial to solve. Oh, crap. It's really trivial to solve this type of system because what do you do? Right, exactly. So, in previous linear algebra courses, this may have been the way to go, or even have ones on the diagonal, so then you just automatically know your right-hand side is your unknowns. But so then the algorithm to solve this, well, you can see easily that x1 is b1 over a11 up to x3. So you could just say 4I equals 1 up to n.
You just wouldn't have to do the subtracting at all.
Right, you wouldn't have to do the subtracting. So that means we don't need that inner loop to loop over the ones that have to have subtraction. So we have bi over aii and then n. So this is a really trivial system to solve, but we won't really be solving systems like this in this class. Like I said, we want to just reduce it to upper triangular form because it's just way too expensive to try to reduce it all the way down to diagonal form. And then the third type of system is lower triangular systems, and we're really not going to talk about those at all today except for, you know, what their structure looks like. We talked about that in the beginning. And lower triangular systems are going to come up when we get into the LU factorization next week. So, but just know that they're solved very similarly to upper triangular systems with something called forward substitution instead of back substitution. So we start at the top and then go down to the bottom. All right, so now we're going to move on to Gaussian elimination. the same Gaussian elimination that you learned in your linear algebra class. So the first thing when we talk about Gaussian elimination is we discuss row operations. Row operations are how we eliminate those elements and get all of our zeros so we can get our upper triangular form. So there are 3 row operations. Can anyone tell me what those 3 row operations are?
One is exchanging the rows, right?
Yeah, so.
That's probably number 2.
Adding a multiple of 1 with
Right, okay. I'm going to write it. When we talk about this operation, I'm going to say subtracting a multiple of one row from another just for consistency, but it's the same thing. And then the last one, does anybody know? It's just multiplying both sides of an equation by a scalar. Okay, so for the purposes of today's lecture, the most important row operation is going to be number 2 right here. That's the one that we're going to use when we're describing this Gaussian elimination algorithm. And when we do our example, that's the one that we're going to use too. Later on, we'll get into exchanging rows. That's called pivoting, but we're not going to do that for a couple of weeks. So this is really the only row elimination technique that we're going to be using today. So what we're going to do now is just, I've got an example, and we're going to work it out, kind of like we did with back substitution, but this one we're going to work out with numbers to see how Gaussian elimination looks, and to see if we can recognize a pattern for when we come up, or for when we try to come up with the algorithm for Gaussian elimination. All right. We have x1 plus 2x2 plus x3 is equal to 5. 3x1 plus 2x2 plus 4x3 equals 17. And then 4x1 plus 4x2 plus 3x3 equals 26. Alright, so this is our system of linear equations, and we're just going to do row reduction until we get what type of form? What type of form are we looking for? Upper triangular, right. So when we start this Gaussian elimination process, what's the very first element that we want to try to zero out? Just from previous 320 or previous linear algebra experience, what do you think would be the first one? Well, we don't want anything above the diagonal, right? So those are all going to remain the same. Which one should we start working on first? Do what? Which one?
3x1.
Yeah, that's the one we want to zero out first. So what would I do that? What row operation can I use to do that? Like specifically, which row times which number?
3 times the first row, and you can subtract that.
Right, so I'm going to say row 2 minus
3 row 1.
3 times row 1. So when I do that, row 2 minus 3 times all of these, then I'm going to get x1 plus, doesn't affect the first row, right? We're just affecting this second row. It's 5, and so this is the one that we made 0, and then it's going to change everything after that too, because we multiplied this row by 3, and so this R2 minus 3 times R1. So that is minus 4x2, right, and then this is 2. Okay, and then everything else remains the same. So, now that we've eliminated this one, which one we want to move on to next to get rid of?
4.
Right, so we want to get rid of this one next. So as I'm talking about which indices or which numbers or which elements we're eliminating, you want to think about what are the indices of those and how does it relate to how I would come up with this in an algorithm, and also think about which ones are actually getting updated. Those right there, everything after this row that we're working on, or this column that we're working on. Alright, so what would I do to eliminate this one right here?
4 times the first row.
4 times the first row, this one minus 4 times this one.
Yeah.
Okay, so I'm going to write it right here. R3 minus 4 times R1. And we've got room over here. So when I eliminate that one, it's going to affect everything in the third row, so everything else remains the same. Alright, so we get 0 here, minus 4x2 minus x3 equals 6. Alright, so which one are we going to look at next to eliminate? Yep, this one right here is the one we're going to get rid of next. So what do I do to eliminate that element?
Subtract row 2.
Right, so we have R3 minus R2. And then that's just going to update the bottom row. And then we get 0, 0, and this becomes negative 2x3 is equal to 4. So do I have anything else to eliminate now? No, because we've got it in the upper triangular form, right? So now this looks just like the system that I started with when I did back substitution. So if we wanted to continue to solve this, we just use back substitution, and I'll go ahead and give, I think it gives the answers to this system in the notes. So, the system that we have is the upper triangular system, and the third equation only depends on x3. So then once we find x3, we can find x2. Once we find x2, then we can find x1. And that should be an x1 right there. There was a mistake in the notes. Make sure. Yeah. So our unknown in the first equation is x1 there. Alright, so now we can see that x3 is equal to negative 2 if we divide, and then x2 is negative 1, and x1 is what? 1. Right. Alright, so we found our solution. So So now that we've done that by hand, we want to talk about how do we do it. How do we do it for a general system on the computer? Because this is a numerical analysis. Now one thing that we can talk about for a minute too is when we did that example, if we were doing that in matrix form, it would be on the augmented matrix, right? So every time we did something to a row, it happened to the corresponding row in the right-hand side vector. But typically when we do Gaussian elimination, it's better to go ahead and do Gaussian elimination on just your matrix, not on necessarily an augmented matrix. And the reason for this is, what if you had, you want to do Gaussian elimination on, or you want to solve a system that has changing right-hand sides, but it has the same matrix A. Then you're going to do all of this computational work on the matrix A, but the only thing, then we can go back and just change our right-hand side and perform the solutions to get with back substitution. So in general, you want to just do it on your matrix A, and then we'll update B as B changed, and then solve our system from there. And Dr. Lambert said that y'all actually, an example that y'all can see this in was y'all were solving linear system of ODEs using implicit method like you did in homework 1. So y'all had like a matrix that stayed the same and the right-hand side kept updating. Is that right? Okay. So let's take...
It's been a long time since homework 1.
Really?
The one in class.
Alright, so let's take a look at the algorithm for Gaussian elimination now. Okay. So when we did this example, we want to look at where did we start. We have 4. I'm going to end it down here. This lines up. Okay. So we want to look at where does this algorithm start at.
3x1.
Right, it started with 3x1, and that's in the first row. So it's the first column, I'm sorry. So it's the first column, and we start below the diagonal with the row, right? So our columns are going to be in the first row, or start in the first column and then loop through to the end. But do we go all the way to the end with this? Do I want to go through every single column? Right, it'd be through n minus 1, because we want to save our last diagonal element. We don't want to eliminate anything in that last row. All right, so it's going to loop over the columns J, so 1 through n minus 1, and then as soon as we loop over the columns, the next thing we want to do is decide which row we're going to be in. So which row are we going to be in?
I plus 1. J plus 1.
Right, J plus 1, because it's going to be the row right after the column that you're working in. So for I equals J plus 1 all the way up to n. So we want to work on every row. We want to go all the way down to the last row. And we'll end this loop. Okay. So now we're going to have something in here, but I'm going to skip that for now. We're going to need another loop as well. We're going to need another loop because what's going on is I now have a row and a column to keep up with where I'm at and what I'm eliminating, but what about what I'm updating? What do I have to update here?
The row that
right, the row that we're in. So we need to know which, so it's going to be whatever row that we're in, but I need to know which columns to update. So we've got 4. I'm going to call this one K. So K is going to, actually, let me draw a diagram up here too of what's going on. So if I have, I'm in row I, I'm in column J. So here I have Aij, and it's below the diagonal. So this is, we can call that Ajj. And here, this is in the same row, but it's in a different column. And this one's in a different, this is in row J, column K. So, what's going on here now is we need to figure out how to keep up with the columns of what we're updating. So, over here in this example, let's look at, this is the first step that we did. So once we eliminated this, we had to update everything after that. So similarly, how we move through the rows is how we're going to move through this column as well, or move through these columns. So what do y'all think we would have for to loop over for these for this loop for K to update it? So which element are we working on? Okay, so we've eliminated right, A12, and then we need to update A22. So here I would be 1 and J would be 2. But we need a new loop to keep track of these. So K is going to be J plus 1. So here's A12, and then we need to update A22 and A23 as well. So and so let me write this down. So K.
J plus 1 up until N.
Right, J plus 1 up until N is what we have to update after that. J plus 1, comma, is what we have to update. So does that make sense how that's what we're updating after this, so that why that's the column index for what we're updating for everybody? Yes. Okay. All right. So now we have our third loop, and yeah, we can go ahead and that one too. So inside this loop right here is where the main step of Gaussian elimination comes from. We've got our row index and our column index, and we've also got what we're going through to update all of these new elements. So what is the main step of Gaussian elimination? The row operation, right? And which row operation were we using? Subtracting a multiple, right, of one row from another. So our new element is going to be Aik. And what do we do to update Aik? We subtract something, like you just said, subtract a multiple of something from another row. So what we're multiplying, I'm going to call it Mij, and that's the multiplier. So it's the number that we multiply. And we'll figure out, that's what we left this space for right here, is to figure out how do we come up with the multiplier first. And then we'll use the multiplier in this step down here. All right, so now let's use
Ajk, or Mij times Ajk, right?
exactly Mij times Ajk. So that's what I was gonna about to do over here with the diagram. But we multiply Mij times Aik and subtract it from this row up here. I'm sorry, Aik minus Mij times this. So Mij gets multiplied by everything in this row, and then we have our subtraction. So that's the main step of Gaussian elimination, and that's the only thing we have in this loop right here. But from that expression, now we can come up with something so that we can actually find our multiplier. So if we look at this step, but outside of this loop, it's just Aij. So for something up here, Aij is equal to Aij minus Mij Ajj, right? So this is for before we get into this loop. So before we get into this loop, what are we doing with everything? We're just zeroing everything out, right? And this is the loop that actually updates everything in the upper triangular part of the matrix, right? Okay, so what should this be equal to then?
0.
Right, it should be equal to 0. And I have Aij minus Mij Ajj. So I want to know, I want an expression for Mij, so now I can just solve for it. So Mij is equal to Aij divided by Ajj. So that's how you come up with your multiplier, which is what you multiply all of these rows by, so that you can eliminate your elements. So we're going to plug that in here now. And Mij is Aij over Ajj. So this is how we came up with our multiplier right here. This is, we just took our expression outside of the K loop, and then since when we're not updating all of those columns, it's supposed to be equal to 0 because those are everything that's below the diagonal. So we set it equal to 0, and then we're just able to solve for Mij. All right. So we're almost done. Let me move these around a little bit. So we ended this loop here, and we also ended that one. So now we have one last step, and this is, if we were working only on the matrix A, getting it into upper triangular form, then we would be done here. So if we want to add in another step, then what's it going to be involved in? It's going to be updating the right-hand side. Yeah, so that, that was good. So if we want to go ahead and work on an augmented matrix and update the right-hand side, then we need one more step. Let me see. So whatever we did to all of these guys in the matrix, we also have to do to B, right? So it's just going to be really similar to that. So we would have BI equals BI minus our multiplier Mij divided by Bj. So this would be our Gaussian elimination algorithm with the updated right-hand side. Now, later on when we talk about the LU decomposition, this is implicitly doing forward substitution, which was dealing with a lower triangular matrix. So if we leave that step out, then we would just have to compensate for it later.
Why did we go from BI to BJ?
Because what we are, what we have going on here. So BI, let's look at an example maybe. So to get this, what we did, we have our row BI, and then we have to divide it by our multiplier times, oh, I'm sorry. Mij, I'm sorry, maybe I wrote this out wrong. Yeah, it's Mij times Bj, not divided, first of all. But it is Bi, oh, and I did this it should be inside both of these loops because we do need the I and J indices. So BI is the one that we're working on, the one that we want to update. So what do we do?
Oh, that's the multiplier times the whatever row that we're multiplying by.
Right.
The B element.
Right. So we have BI here, so B is 2. And then we say BI is, so how did we get this? We said
17 minus,
right.
like 3 times 5, right?
17, right, times 3 times 5. So that's why our multiplier is multiplying the row above it to get to update this right here. So J is 1, I is J plus 1. So the one that we're updating is here.
Yes.
So we're multiplying by that to get that one there. Okay. So now that we've gone over Gaussian elimination, how many nested loops do we have here? 3. So in cubed, but actually there's a constant in front of this one, 2/3 n cubed. Write this. Floating point operation. So to come up with that constant, I think it's kind of rigorous and we're not going to do it in here. But you can see from the nested loops that we do have n cubed, but 2/3 n cubed is the number of floating point operations it takes. So like I was saying before, we don't want to go through 2/3 n cubed operations unless we have to. So we're gonna get our matrix into upper triangular form, and then if we have to solve different systems with varying right-hand sides, then we're just gonna go back and do back substitution. Actually, we would have to do forward substitution, which is this step right here, and then back substitution as well. But forward substitution is n squared operations, just like back substitution is. So it's better to do the 2/3 n cubed operations only once, and then you repeatedly do your n squared operations after that. So if we have forward and back substitution, it would be 2n squared, but that's still better than 2/3 n cubed. So let's see. And also another thing about this implementation of Gaussian elimination, we're never actually explicitly zeroing anything below the diagonal, because we know that when we do this operation, then everything below the diagonal is going to become 0. So we're just saving that space right now. We're not going to actually explicitly zero everything. All we actually do is update the diagonal and update everything else, so we can solve for our system. We're just assuming that everything below the diagonal is 0. And then we'll get into the lower diagonal part, the lower triangular part, when we get into the LU factorization next week. Alright, so there's one more example, but this example I was going to save to do in the lab. So I think that's all that we have for today. Are there any questions about anything right now? Alright. Well, y'all are free to go then.